Okay, today we're going to talk about bits and bytes. So we're going to be talking about the bits and the bytes that make up our data, or variables. All variables in memory are represented with a group of bits in memory. So a bit is simply a 1 or a 0. And a byte is a group of 8 bits. Multiple bytes can be grouped together. So for example, an int on most machines is 4 bytes, or 32 bits. Some data types are made up of many, many bytes. Okay, the smallest data type, however, the character, is 1 full byte. So 1 byte is the smallest unit of memory that we can access from our program. So if your machine has 8 gigabytes of memory, your program may use any one of the 8 billion or so bytes to store data. Okay, so simple types are ones that can't be broken down into smaller pieces. So int, float, character, those are all simple or atomic data types. Strings are not simple, arrays are not simple, and structs are not simple. None of these are simple or atomic because they're composed of smaller units and can be broken down into their components. So a string is a collection of individual characters, an array is a collection of data that's all of the same type, and rather than having a name for each piece of data has an index from the beginning of the array. And a struct is a collection of individual data members, where each data member does have a unique name, and the different data members can have different types. Okay, that's different from the array. In the array, all the elements of the array have to be the exact same type. With a struct, you can mix the types. Okay, each data member can have its own type. Okay. Let's talk about the integer. Okay, so the integer is one of those simple types. Turns out there are different types of integers. We have a character, a short, an int, and a long. So we talked about the character type. It actually is an integer that really the only difference between a character and any other integer is that when we print out a character, instead of printing out a numeric value, we go to the ASCII character set and we actually print out a letter, okay, or something from the ASCII chart. The only real difference between the integer types, other than that one difference with the character, is the number of bits that variables of these types take up in memory. So the number of bits in one of these integer variables determines the range of values that can be stored inside them. Okay, so you can actually use any one of these types. We haven't looked at short or long in class, but if you certainly can use them. Okay, so we have character is a 1 byte data type, a short is 2 bytes, an int is 4 bytes, and a long is 8 bytes. And the number of bytes determines the range of values that can be stored there. So if we look at a character, the range of values is from about -128 to 127. A short, a 2 byte integer, is from about -32,000 to about +32,000. A 4 byte int is the range of values is about from -2 billion to +2 billion. And an 8 byte long, this is a really large number. I believe this is about -9 quintillion to +9 quintillion. So that's a really big number. Okay, most of the time we use the int data type for integers. And it turns out we can use these things called int min and int max. These are constants to check the upper and lower range of the data. Okay, so we know int min is this value and int max is that value. So you can use these in your code if you want to, for example, store the largest possible integer that could be stored inside an int. You can do something like this in your code. Okay, so what would happen if you added 1 to x? Whoops. So x is equal to x plus 1. Okay, well that would cause something called an overflow. So I think we talked about this in one of the earlier videos. Each data type, each integer data type, has a certain range of values. So this number line here, that's int min over here, that's int max. Right? We know when we add, that pushes us to the right on the number line. So if we're at int max and we add 1, if we try and go 1 beyond here, the way it works is this number kind of wraps around itself. Okay, so if we were over here at the end and we started adding and we ever crossed that boundary, we'd add a number and actually end up with a much smaller value, something in this range over here. Okay, and that's called an overflow. And that's usually a very bad thing. Okay, so if you're using really big numbers like that, well, you might want to choose to use a long, because the long has a much larger range of values. Okay, there happens to be a way to find out how many bytes are in a particular data type or a variable by using this thing called the size of operator. Okay, so again, within your code, size of is kind of a built-in thing here. So if you said size of character, this kind of looks like a function call. It's kind of like asking a question, well, what is the size of a character? Well, that's 1 byte. What is the size of an int? Well, that's 4 bytes. You could also use just the name of a variable. So here are data types. This is actually a variable. The size of x, well, x up here was declared as an int, so we know that's 4 bytes. And if we created a student type, maybe we had a struct for a student, the size of the student is really dependent on how we defined the student data type, which I didn't include here. So it might be 16 bytes, it might be 100 bytes, depending on what data members we put in that student struct. Okay, but right now, we don't really know what the bits mean. So we know that an int has 32 bits, it's a 4-byte data type. But we don't really know what those bits mean. That's what I want to talk about today. Okay, so the first thing we have to talk about is that the computer uses binary numbers instead of decimal numbers. So humans use a decimal numbering system with digits 0 through 9, presumably because we have 10 fingers and very early humans relied on those fingers to count things. Computer, of course, does not have any fingers. What a computer does have is this ability to distinguish between high and low voltage. Therefore, a computer uses a binary numbering system with 2 digits, 0 and 1. These two values represent high and low voltage, okay, which is the only thing really the computer can understand. Okay, so we have the decimal and the binary numbering systems. There's another numbering system that computer people sometimes use. It's called the hexadecimal numbering system. Okay, so let's kind of review what we have here. We know a lot about the decimal numbering system. There are 10 digits in it, and the 10 digits are 0 through 9. Okay, you may have heard of the binary numbering system. There are 2 digits in this one. They are 0 and 1, basically. And then hexadecimal, this is kind of an oddball one. You probably haven't heard about this one. But it has 16 digits, and the values are 0 through 9, so the first 10 decimal digits, then A through F, where A means 10 and B means 11 and so on. Okay. In other words, the range of values is from 0 to 15. Okay, so we all know about the decimal numbering system. Let's learn about the binary numbering system. And you can apply everything we talk about here to teach yourself the hex numbering system too. I'm not going to spend a lot of time on that. Okay, so let's start by looking at a number, maybe the number 495. It's a nice decimal number we could look at. Okay, so what is this number, 495? Well, we could think of this as 490 and 5. Or in other words, 400 plus 90 plus 5. That would be an accurate way to think about the number 495. We can extend this even further. We can say, well, this is really 4 times 100 plus 9 times 10 plus 5 times 1. And you might have noticed that we have a single decimal digit here, multiplied by a power of 10. So we could break this down even further and say this is really 4 times 10 squared plus 9 times 10 to the first power times 5 times 10 to the 0th power. So 10 squared is 100, 10 to the first power is 10, and remember, any number raised to the 0th power is 1. Okay, so the powers of 10 always start with raising 10 to the 0th power in the least significant digit. In this case, the 5 is the least significant digit. And what happens then is we increase the power of 10 by 1. Each digit we go to the left. So every additional digit is really, we're taking that one digit and multiplying it by a slightly higher power of 10. Okay, it turns out the binary numbering system does the exact same thing, but it uses a different base number to multiply. So instead of base 10, we're going to use base 2, and there are going to be fewer digits. Instead of having the 10 digits 0 through 9, we're just going to have the 2 digits 0 and 1. Okay, so before we look at how this works, let's go look at some powers of 2, just to remind ourselves. Okay, so remember I said anything to the 0th power is 1, 2 to the first is 2, 2 squared is 4, 8, 16, 32, 64, 128, 256, 512, and 2 to the 10th power is about 1,000. It's actually 1,024. Okay. So basically you start with a 1 and you just double it. So 1, 2, 4, 8, 16, 32, 64, and so on. Okay, so let's try and interpret a binary number here. Let's take the number 1101, binary 1101. Okay, and let's just apply the rules that I talked about before. We're going to take each one of these digits, there's 4 digits in here, and we're going to multiply them by powers of 2, where the least significant digit, the one over here on the right, we're going to start at 2 to the 0th power, and 2 to the first, 2 squared, 2 to the third. If I had more digits, I'd have 2 to the 4th, 2 to the 5th, and so on. And then we just multiply the digit, either 0 or 1, to that power of 2. So the nice thing about this is all the zeros, 0 times anything is just going to give us 0. So 1 times 2 to the 0th is 1 times 1, or 1. 0 times anything is 0. 2 squared is 4. 1 times 4 is 4. 2 to the third is 8. 1 times 8 is 8. So we can now add these things. 8 plus 4 plus 0 plus 1 is 13. Okay. So binary 1101 is equivalent to decimal 13. Each are just symbols that represent the same quantity. Okay, so when we talk about binary versus decimal, they're all just numbers. These are just different symbols, different ways of representing the exact same thing. Okay, so now I want you to try this here. So I want you to pause the video and try and calculate the decimal equivalent of 100101. Okay, so pause the video now, and then I'll come back and explain the answer. Okay, so it turns out 100101 is equivalent to decimal 37. Okay, so how did I do that? Well, again, I just started with my powers of 2. 2 to the 0th, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. And then really what I did was I just looked for the 1s. Anywhere there was a 1, I pulled that power of 2 down. So here's a 32. My next one was here. That's a 4. My last one was over here. This was a 1. The zeros, you don't even have to bother calculating the power of 2 because 0 times anything is going to be 0. So this becomes 32 plus 4 plus 1, which is 37. Okay, so a shortcut to do this in your head is just start at the far right and then move one digit to the left. Start with the number 1 and double it as you go along. If there is a 1 at that position, you add that power of 2 to the sum. Okay, in other words, you start at 1, or you start at the far right, and you say, all right, there's a 1 there. Right, we know this is 1, 2, 4, 8, 16, 32. So 1, 4, and 32. That gives us a value of 37. So it's kind of a shortcut because there are only 2 digits and one of them is 0. You really just have to look for the ones, and then if you start at 1 and continue to double each time you move to the left, it's a pretty straightforward way to translate a binary number into a decimal equivalent. Okay, so now we know a little bit about the binary numbering system. That's really all it is. I mean, it's exactly equivalent to the decimal numbering system, except we use 2 digits and base 2 instead of 10 digits and base 10. But now we should be able to count in binary. And that's what I'm going to do here. So this represents 1. So binary 1 is equal to decimal 1. So what's this? Well, this is 2. Right? So it'd be 1, 2. This is the first one. So that's how we say decimal 2. This will be 3. So 1 and 2 is 3. 1, 2, 4 tells me this is 4. 1 and 4 is 5. 2 and 4 is 6. 1 and 2 and 4 is 7. 1, 2, 4, 8. 1, 2, 2, 4. 1 and 8 is 9. 2 and 8 is 10. And so on. So this is basically counting from 1 to 10 in binary. And after you do this enough, you can actually start to do it pretty quickly in your head. Okay, so there's this kind of really old, kind of lame joke that says there are only 10 kinds of people in the world, those who know binary and those who don't. Okay, most people see the 1, 0 as a 10. We, of course, now know it to represent the number 2 as well. Right, so 1, 0 in binary is 2. Okay. There's an algorithm to go from decimal to binary, too. We just went from binary to decimal. Sometimes it's useful to go in the other direction. So basically what you do is you repeatedly divide a decimal number by 2 and store a remainder. Okay, then we're going to take the quotient and divide that by 2 and just repeat. And we're going to stop once we get to a quotient of 0. So let me show you. It's probably a better way to explain this. Let's say we have the number decimal number 13, and we want to convert that into a binary number. Well, we're going to divide by 2. So 13 divided by 2 is 6 with a remainder of 1. Okay, then we're going to take that quotient of 6, and we're going to divide that by 2. 2 goes into 6 3 times with a remainder of 0. Then we're going to take that quotient divided by 2. 2 goes into 3 1 time with a remainder of 1. And then we're going to take the quotient of 1 and divide again. 2 goes into 1 0 times with a remainder of 1. Okay, and then we stop here. Whenever we get a quotient of 0, we know we're done. And basically, these remainders, because we're dividing by 2, the remainder is always going to be either a 0 or a 1. Okay. The only weird thing is we take these remainders in reverse order. So it's 1, 1, 0, 1. 1, 1, 0, 1. Okay, and you could kind of prove yourself that this is correct. So this would be 1, 2, 4, and 8. 8 plus 4 is 12, plus 1 is 13. Pretty sure that 1101 is equivalent to decimal 13. Okay, so why don't you try? So I'm going to give you this number 137. So I want you to pause the video and turn this decimal number into a group of bits. Okay, so remember our number was 137, so we're going to repeatedly divide. Okay, we get 68 with a remainder 1, 34 with a remainder of 0, 17 with a remainder of 0, 8 with a remainder of 1, 4 with a remainder of 0, 2 with a remainder of 0, 1 with a remainder of 0, and 0 with a remainder of 1. Now I have to do these in reverse order, so we have 1, 0, 0, 0, 1, 0, 0, 1. And that's what I have here. Okay. And again, we can check our work by saying, all right, well, here we have a 1, 2, 4, 8, 16, 32, 64, 128. Okay. 1 plus 8 plus 128, that actually is 137. Okay, so this idea of changing the numbering system just by using a different base number and a different number of digits works exactly the same for the hexadecimal numbering system. Okay, so it turns out the number 14EF doesn't look like a number because it has some letters in it, but if we're talking about the hexadecimal numbering system, this is a number. And if we convert that to decimal, that's 5,359 decimal. And we could take that and convert that into binary. And if I did that correctly, it should be 1010011101111. Okay. Okay, so why are we learning about this? Well, with all the signed integer types, remember the difference between them is the number of bits that make them up. Well, if you look in memory at any one of these integer types, one bit is used for the sign of the number, and all the other bits are used for the actual number. Okay, so for example, here's 32 bits that might represent an integer. Okay, and again, we have that one sign bit. So this will be a 1 or a 0, maybe 1 means positive, 0 means negative, and then we have 31 bits for the entire rest of the number. Okay. So 2 to the 31st is about 2 billion. That's why the range is plus or minus 2 billion or so. The sign bit tells us whether it's a positive or a negative number, and the remaining 31 bits are just used to hold an integer value. So you can kind of imagine 32 ones or zeros, all those powers of 2. You could, if you had enough time, take any 31 bits like we have here and convert those into a decimal number. Okay, so that's really all an integer is. It's that one sign bit, and then the rest of the bits are used to make up a whole number. Let's talk about floating point numbers. So every float is actually made up of 4 distinct parts. Okay, so let's start with looking at this number minus 0.0023756. Okay, looks like a good real number here, right? So it has a fractional part. Well, another way to think about this is really the number minus 23,756 times 10 to the minus 7th. So if we imagine this whole number here, right, has a decimal point, if we move this over 7 places to the left, 1, 2, 3, 4, 5, 6, 7, that would give us our 2 zeros there. Okay, so this really is just another way of thinking about this number, minus 23,756 times 10 to the minus 7th. Well, basically all a float is it grabs the 4 pieces of data here. So we have the sign of the number. Okay, again, that'll be just 1 bit, either a 0 or 1. We have the sign of the exponent. So the exponent could be positive or it could be negative. So we have a bit for that. We have our base number, and again, this is going to be some number of bits that represent an integer. And then again, these will not be decimal digits; these will be binary digits. But I'm using decimal digits just to make my point here. And then some number of bits are set aside for the exponent. Okay, so a float is, like I said, these 4 bytes or 32 bits of data. There's another type in C++ called a double, which is, again, very much like a float, except it is 8 bytes or 64 bits per piece of data. And again, this is on most modern machines. Okay, so we'll see that integers really are different than floats, because an integer was just one sign bit and then 31 bits for the number, whereas a float has these 4 different compartments. Okay, unlike integers, you can't always specify every single value inside a float. So let's imagine a new data type that has only enough room in the base number for 3 digits. Or in other words, the base number could only hold between 0 and maybe 999. Okay. Well, if that was the case, how could we represent a number like this? 0.123001 or 0.123999. Well, we can't, because we really only have room for 3 significant digits. And we should take the 3 most significant digits to get the most accurate approximation. So if that was the case, if we could only store 3 digits, we're going to grab these 3. Okay, not the least significant digits. We want the most significant digits. So both of these numbers would be treated as 0.123. Okay, so we've already kind of run into this when we ask the computer to divide numbers for us, for example. So if we take float 10 divided by float 3, we know the real answer is 3.3 repeating, where the number of 3's really is infinite. Okay, but now you could see, well, if we only have 32 bits, and we need a bit for the sign of the number, a bit for the sign of the exponent, okay, our integer value might be some number of 3's, however many 3's we can stuff in there. And then the exponent, there's always some room set aside for that. Okay, so again, this if we move this over 5 places, 1, 2, 3, 4, 5. Okay, this is how we represent 3.33333. And again, this is close to, but not exactly, 3.3 repeating. Okay, so hopefully this removes some of the mystery of what the computer does. Ultimately, remember, all a computer can do is add numbers, compare numbers, and move numbers around to different places. So even the text that we use whenever we surf the web or we write in a word processor, to the computer is really just a bunch of numbers stored inside the memory. In later classes, we'll talk about how we do the arithmetic, the adding of numbers, and the comparing of numbers. But it's all fairly mechanical. It's all, I think, not terribly interesting. It's certainly not magic. And that was the main point of this lecture, is to kind of prove to you that there's not any magic happening inside the box. This is all pretty straightforward stuff.